Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is, I can't tell what. It's too bright in here for me to see it. Okay. I've become paranoid about whether or not the camera is actually pointing at the whiteboards. Let's see. So I'm done grading your exams. I'll have them to return to you tomorrow. I haven't recorded any of the scores yet. I finished grading them this morning. So
how did we do as a class?
there were a bunch of scores in the 70s. I think there was one that made it up to 80. There were a bunch of scores that were well below 70. So.
Is there some in 30?
Let's see. So Monday is a holiday. So that cost me a day of lecture that I hadn't adequately budgeted for. So I'm gonna remind us from last time that for an adiabat, we had PV to the gamma is constant. And we also had that T times V to the gamma minus 1 is constant. Not the same constant, but constant nonetheless. I had intended to derive this for you, but I'm picking and choosing a little bit. I'll leave looking up that derivation to you because it's in your textbook. In the interest of stealing back a few minutes and focusing on stuff that I think will serve you better. So I also wanted to broaden our discussion a little bit. So we have focused thus far on ideal monatomic gases. And I wanted to at least add to our repertoire diatomic gases. And so for monatomic ideal gas, we had that CV was 3 halves R and CP was 5 halves R. And then let's add to the mix a diatomic. Ideal gas. CV is going to wind up being 5 halves R, and CP is going to wind up being 7 halves R. Effectively, remember from, I don't know, like a week and a half ago at this point, that each degree of freedom that we added allowed for 1/2 kBT.
7/5.
It is, yeah, sorry. Each degree of freedom that we added afforded 1/2 kBT, right? And so for a monatomic gas, the only bin we gave it was translational kinetic energy, right?
That's 7/5.
It is. Um, the every degree of freedom added 1/2 kBt. For an ideal non-atomic gas, we said that the only bin that we were giving it was translational kinetic energy. How many independent axes are there for translational kinetic energy? 3. And so we had 3/2 kBt, right? If we add a diatomic gas, and for now, let's ignore vibration. Let's assume that that doesn't occur until you get to much higher temperatures than we're going to be interested in for the time being. Then we could roughly model this as 2 atoms connected by a spring or a stick, right? And if I wanted to consider rotation, right, we're ignoring vibration, we're going to treat this like some rigid stick so that it can't, there aren't modes to worry about in this sense. How many independent rotational axes do we have?
3.
Not quite.
We have 5.
Well, I'm seeing 2. We could rotate about this, right? We could rotate about an axis sticking out of the board. The 3 answer, I get where that's coming from.
We have 3 axes, so
Because
what happened to the third one?
what happens if we try and rotate about this one?
Same thing.
Doesn't look any different, right?
But still a rotation.
But it doesn't look any different.
Because you can't tell one side of an atom for the other. So
The atom doesn't have a front side and a back side, right? So if I peeled the label off this pen and rotated it, you couldn't see my hands, took off these little stubs, it'd be hard to see that it was actually rotating, right? It's kind of what I'm arguing here.
Okay.
The axes that we care about are this one and this one, right? If I spin it around this way, we'll know. If I spin it around this way, we'll know. Does that make sense? So we're adding 2 more kBt. So we went from 3/2 to 5/2, right? We had the 3 before y.
Vibrational.
The 3 before were coming from the x, y, and z translational. We still have those x, y, z translational, but for the diatom, what else do we have? Well, we've got those 2 rotational axes also. Does that make sense? So, if we were plotting CV against T, what we see is something like this. And this step is actually pretty pronounced higher. I guess I have to put it here. Does that work for you? Okay, so that's somewhat further out there than I've drawn it, but
Does that mean CP is 7/2?
yes. I'm sorry. Is that why you guys kept asking if?
Yeah.
Yeah.
You say 5 years.
That was definitely my 5, but that wasn't what I meant. Thanks, guys.
That makes sense.
Yeah, that makes sense.
Okay, Questions, comments, concerns?
What's this? The wiggle line is for the,
Those,
is the
we're
track?
looking at
Uh-huh.
the specific heats,
Oh, okay.
the molar specific heats as you change the temperature.
Uh-huh.
Low temperatures, you don't really have to worry about the rotation, it's just the translation.
Uh-huh.
At kind of intermediate temperatures, you have to worry about the rotation and the translation for the diatom.
Oh, okay.
At pretty high temperatures, then you have to start worrying about vibration also.
Oh, okay. So
Yay, enough.
This is for high temperature, you mean this graph?
No, the temperature was the horizontal axis, right? So you don't have to worry about the step up to include the vibrations until the very end.
Oh, okay.
We're okay? All right. So I feel like our time is going to be better spent on looking at heat engines, which means that we need to spend some more time on the cyclic processes. I don't know if anyone watched the
Recordings.
recording from yesterday, but I did several problems involving using the first law in practice, and a couple of them I think dealt with cyclic processes. So definitely give that a look, because
Do you have
It's a
every
Tuesday.
Tuesday have a workshop here?
uh-huh.
Oh my god, okay. I missed $100 million every day.
No, you didn't miss anything. They're on YouTube, so. And the joy of YouTube is you can speed it up to twice as fast.
Oh.
It's still a monotone, but it's like a higher pitched monotone.
Yeah.
Um, Get through it twice as fast, too. You can fast forward through all of my horrible attempts at humor. I want to describe the efficiency of a heat engine. And so, what do we want an engine to do?
To work,
We want it to do work for us, right?
yeah.
And so,
Don't lose energy.
what are we spending in order to do that?
Heat.
The engine-
We're pulling energy as heat out of a high temperature reservoir. So when we speak of the efficiency of a heat engine, we are saying how much work do we do per joule of energy extracted from a high temperature reservoir as heat. Does that work? Is that okay? Then we could assume that there's no losses anywhere. So if we assume that there's no losses anywhere, then the work done should be the heat extracted from the high temperature reservoir minus the heat returned to the low temperature reservoir, and then still divided by the heat extracted from the high temperature reservoir. And so this looks like 1 minus QC over QH. Yay? If we're specifically talking about something called a Carnot engine, after Nicolas Sadi Carnot, then, and I'll try to demonstrate this for you. I'll probably try to use part of our problem session on Tuesday to demonstrate this for you. But for a Carnot engine, we could write this as 1 minus the high temperature, 1 minus the low temperature reservoir temperature divided by the high temperature reservoir.
How do you spell his name?
Carnot? So this is true. Again, ignoring stuff like friction. But here, this will be true only if you're talking about a Carnot cycle. Is that kind of all right? Maybe I should put this in brackets. So I'm okay with this guy, right? But this is for a special case. Yay? Okay. If we were talking about something like a refrigerator, we would talk about the coefficient of performance. And there, what we care about is how much heat we can extract. And so the coefficient of performance here is how much energy we can extract from the low temperature reservoir and how much work did we have to spend to make that happen. Is that all right? Okay. Okay, so then I used more board space on that than I intended. Probably should have put that on the other board, but oh well. With that in mind, I wanted to look at the Otto cycle. So there's a few cycles that are commonly used to model combustion engines, like what you find in cars, at least pre-electric cars. And so I'm going to try the Otto cycle for you, because I think that, the diesel, as it sounds like, is a better representation of the diesel cycle. The Otto cycle is a better representation of a combustion engine that employs a spark plug. And so that's just the one I picked. But maybe next Tuesday, depending on how things are going, we'll also include an example with the diesel cycle, just for extra practice.
Are all combustion engines not gasoline?
So I wouldn't put diesel fuel in my hybrid. I would be sad about that.
Yeah.
So they're all combustion brands of heat engines,
Right,
but
you-
the process is different.
Yeah, that's why you separated diesel from combustion.
It's a different type. So in a diesel engine, I'm not using a spark plug. So there's a difference in the compression stroke. Let me show you the Otto cycle, and then I'll show you how they differ.
Okay.
If you want to see how the diesel stroke is different, I will try to, I'll try to add that to Tuesday's problem session video.
Okay. So 3:30.
Or you can just take a picture of my notes, because I did it there.
Oh. I'll do that too.
I'm gonna skip it, but, for today at least. So, the auto cycle, it's a good model of spark plug based combustion engine. I'm probably gonna fail miserably at modeling this, but it's not my worst. Sadly, you've seen my worst. So we're going to connect a pair of adiabats by a pair of isochores. And I call these A, B, C, and D. As I promised you the other day, it's hard enough when you're looking at like actual plotted data to just with your eye see the difference between an isotherm and an adiabat. But with my hideous drawing, the chances are nil. So on something that I actually draw for you, I'll tell you adiabat or isotherm. Okay, so the nice thing about this is there's a couple of, because these are special cases, there's a couple of things we can say straight away. So can you tell me any special features of this?
Parallel kind of.
Do you mean like the work, the heat? Or?
Yeah.
Okay.
So can you tell me anything special about the work or heat in any of the individual steps?
Work is 0 from B to C. And D
So
to A.
work from B to C
Yes.
is 0.
Heat from A to B is 0.
Heat from A to B.
It's an A event, right?
What's that?
It's an A event, so, okay.
What else?
Work from D to A is 0.
Heat from B to C is greater than 0.
What else?
Positive.
There's one more you can give me.
QC to D is 0.
Okay. Then, do you guys remember looking at our PV diagram? If I were just plotting a whole bunch of isotherms, what would they look like? Again, I am a horrible artist, but something like that, yeah? We're happy-ish. Be flatter, huh? Then, how is the temperature changing across these isotherms?
Not changing, it's constant. Oh, from the lower
So-
to the higher?
So as I go this way, what's happening to temperature? Temperature is increasing, right? So everywhere on this is the same temperature, but every point on this is a higher temperature than every point on this, yeah? Yes, no, maybe so?
Yes.
Okay. Then, looking at this, would you be willing to kind of chance a guess at whether TB or TC is at a higher temperature? You don't even need to really chance it because you could just use PV equals nRT, right?
B is higher than C.
Say again?
Is B higher than C?
So C has a higher temperature than B, yeah?
Yeah.
Does that make sense? One way that you could see that, right, is that PV equals nRT, so T goes as PV over nR. They have a common volume, right? But C has a higher pressure than B. Does that work? Okay, so then what happened to delta E internal from B to C?
Increases.
It increased, but we did no work. So what had to happen?
Energy in a set.
We needed heat, right? So in my bad kind of pictogram model here, the way that I'm going to denote that is energy is flowing into the system. That's goofy, right? Because this isn't actually the system, right? It's just the cycle that the system is carried through. But to me, at least in my broken thoughts, what I see is, oh, we are taking energy as heat, bringing it through the barrier into the system, right? I'm drawing it this way, but I do want to stress that this is just my mnemonic device. This isn't the system. This is the cycle the system is passed through, yeah? Okay. Could you make another logic argument about the temperatures D and temperatures A? D has to be at a higher temperature than A, yeah? For much the same reason as C had to be greater than B. But again, we did no work. You guys told me no work done from D to A.
So the energy lose QC.
So this time, we're dumping energy out of the system into a low temperature reservoir. That's kind of our simple model here. So
Does that mean QH equals QC? Or is it because
well,
of
if
efficiency?
QH equals QC, why can we just not bother studying this? It would make an incredibly poor engine, right?
Yeah.
If QH equals QC, what's the efficiency of that engine?
0.
0. And so
You don't want that.
We don't have cars.
So we wouldn't, whoever Otto was, that's horrible. I shouldn't say that on camera. This is what the guy was famous for. We wouldn't remember. Congratulations, you came up with an engine that is 0% efficient, right? But that's not the engine that is proposed here. So, and apologies to the line of autos around the world. We're okay with that. Then which one's going to have to be bigger for us to bother remembering Otto's name?
QH.
And I'm sure he was a perfectly lovely person worthy of having his name remembered regardless. I once got yelled at for, and I didn't even impugn the name of Ben Franklin. I just said he was the amateur scientist because he was. I didn't mean that in a bad way.
I'm sorry, what's the first word you said?
Impugn,
What does that mean?
cast ridicule upon.
Oh, okay.
Call into question his good name. I didn't do that, but I still got yelled at for it. So, but that said, what has to be bigger in order for us to care about this particular cycle, regardless of whose name is on it?
Huge.
Okay. So let's see if we can suss this out. So can I draw? You don't like the word sus either? Goodness. I eavesdrop, I'm sorry. I have to entertain myself somehow. So, I'm not going to draw it on here, but I do want you to have a better picture of what's actually happening. So, A, B, C, D. I'm going to also give myself point O. And so from I guess I'll do it with this. No one's complained yet. From O to A, we're going to draw out the piston and bring in air at atmosphere. I'm really only worried about the oxygen part of this, but we're going to, much like when you expand your chest, right, you draw air in, we're going to do, yeah, yawn, it's good for you. We're going to allow air in at atmosphere. And so this is coming in at constant pressure. So O to A, we're going to intake at P atmosphere. Yay? Then A to B, are we expanding or compressing our newly taken in oxygen or air? We're going through a compression stroke, right? So is that work on the gas or work by the gas? I think I'm an old man, but I think what I heard was work on the gas.
Yeah.
Yay? From B to C, this is kind of where our model is a little bit hand wavy. This is our combustion. Now, how did I say in this Otto cycle we're gonna get combustion? What's the difference here versus our diesel engine? We're gonna need a spark plug. So schools don't offer auto shop anymore, do they?
Yeah, we got it here.
You do? No, I mean like high schools.
Oh.
No, we don't really know it's not true.
It was a standard thing when I was a young person.
My high school had it actually. They
So
just- it was
I'm sad
never-
that they got rid of it.
It was, well, I mean, I wasn't young.
We're moving to electric cars.
Yeah.
Well, I think it's an insurance issue. Like it's dangerous for,
Kids.
anywhere that kids could hurt themselves. It's an insurance liability for schools. So, but I wrecked my first car 2 weeks after I got my license. And by wrecked, I mean pushed the left front fender through the left front tire.
You were a dangerous
And,
kid.
and my parents, I just wasn't a good driver. I'll tell you the story later in the semester. But my parents made me, no, I'll tell it on camera, I've told lots of people. I have no shame. My parents made me take auto shop, and I'm so glad they did. It was one of the most useful things I've taken. Instead of doing this, you can walk across campus. Really useful class. So this is where it's a little hand wavy, because this QH isn't really being extracted from a high temperature reservoir. Instead, what we're really getting is energy conversion. So it's not really the way we're treating it. It's not actually coming from an ideal gas process. It's coming from a chemical process, but it works well enough all the same. So B to C is our combustion process. C to D is what is called the power stroke. So here is our, and when I say gas, I don't mean gasoline, I mean the ideal gas, our oxygen, right, or our air. Is the gas doing work, or is the environment doing work on the gas?
The gas don't work.
The gas is doing work. So. Yay? And then D back to A, we're opening the exhaust valve. So what's happening in that case? What happens to the pressure?
Decreases.
So the pressure is dropping. It will return to what?
Initial state.
It's going to return to atmospheric pressure again. And so then we can draw out the piston again and take in more air. It's the oxygen that we care about, right? But we're going to take in more air and start the process all over again. Is that all right? So
God bless you.
and they all lived happily ever after. At least thus far. Okay, then I'm going to tell you this efficiency, and then we're going to work through this. So the efficiency is 1 minus 1 over V1 over V2 to the gamma minus 1. So if our compression ratio is about 8 and gamma is about 1.4, give or take, then our Otto cycle winds up being about 56%. So about 56%. This isn't taking friction into consideration. So realistically, you're probably getting to around 15 to 20% efficiency. So that's kind of our where we stand. So let's try an example with numbers, just so that you can get a sense of this. So I'm going to be sad about this, I'm sure. So let's look at 3-liter gasoline engine. So let's imagine that this thing has 6 cylinders with a total displacement volume of 3 liters. Let's push this at about 4,000 RPM. And a compression ratio of 9.5. Let's let ambient temperature be 27 degrees Celsius and combustion temperature 1,350 degrees Celsius. I'm rounding liberally enough that without any shame, just told you I have no shame. So, I mean, I did like the twirly rotation thing on camera. Without any sense of guilt or shame, I'm going to round this to 100 kilopascal. This also winds up being 300 Kelvin, right? Okay, so then let's start by saying, in my notes I called this equation 1. Seems kind of wasteful to do that, but VA over VB, what is that? VA over VB is how much I've compressed this, right?
Compression ratio?
And so the compression ratio should be 9.5, yeah? Not really as my 5, and I really intend it to be a 5 this time. With apologies. Although still no shame. So delta V is how much the volume has changed, right? And so that's our displacement volume. And what is that equal to? Well, so we have to be careful. We have 6 cylinders, right? And so we have 3 liters over 6 cylinders winds up being 0.5 times 10 to the minus 3 meters cubed per cylinder. Is that all right? So one thing that we know is that VA minus VB is 0.5 times 10 to the minus 3 cubic meters. And we know that VA divided by VB is 9.5.